Hello everyone, welcome to this presentation of our paper, CommonRoad-RL, a configurable reinforcement learning environment for motion planning of autonomous vehicles. My name is Xiao Wang. This is a joint work with my colleagues Hanna Kroski and Matthias Althoff. We are from Technical University of Munich. This work is published at ITSC 2021. As a motivation, we show here how quickly the number of papers on reinforcement learning for motion planning grows with time. This is the result on Web of Science. However, each paper uses evaluated their methods on their own platforms and on different traffic scenarios. Which makes it very difficult to compare different methods. This was why we developed CommonRoad-RL. Our goal is to bridge the gap between our existing benchmarking platform, CommonRoad, and reinforcement learning research. So let's first have a look at how CommonRoad represents a traffic scenario. A scenario has road network, which in CommonRoad is in lanelet format. The left and right boundaries of the lanes are polylines. We define an initial state and a goal region, which the planned trajectory should start from and reach in the end. We have different types of static obstacles and dynamic obstacles. We also define traffic signs and traffic lights to take traffic rules also into account in our motion planning problems. Currently, we provide more than 4,000 scenarios at our website. And there you can choose different kinds of scenarios, for example, highway, intersection, or merging scenarios. We also provide interactive scenario simulation with Sumo. So here you can see an example how the vehicles behave differently if the trajectory of the ego vehicle changed. In addition, we provide converters to transfer popular traffic dataset to CommonRoad format. Since some of the datasets are publicly available for academic purpose only, currently we support NGSync, HiD, INDI, and interaction dataset. We will continuously develop converters for more popular dataset. So now we know about a bit more about CommonRoad. Let's have a look at its interface to reinforcement learning environments. The first important element is the observation space or state space. We define it in 4 categories: the states of the ego vehicle, the topological information of the road network relative to the ego vehicle. So for example, here, the distance to the left road edge and the distance to the right marker of the ego lane. Since our task is to reach a predefined goal region, we also provide information on the goal region. For example, here, the longitudinal and lateral distance to the goal area. To avoid collision, we also provide states of the surrounding traffic participants within a given sensing range. As for the action space, we have both continuous and discrete action space. The continuous action space is defined as the control inputs of different vehicle models. The inputs of the point mass model are the accelerations in X and Y direction in Cartesian space. The kinematic single track model is also called the bicycle model in some literature, and its input are the longitudinal acceleration and the steering angular velocity. We also have a modified version of this model, which uses the yaw rate instead of the steering angular velocity as its input. The single track model additionally considers the tire slip to include effects like understeer or oversteer. Lastly, we have the a multi-body model, which considers more sophisticated dynamics. We have two types of discrete action space. One is the discretized control inputs of those vehicle models. The other one is the high-level planning decisions, which are executed by a sampling-based trajectory planner. We terminate an episode if the ego vehicle collides with others, if it reaches the goal region, if it drives outside of the road, or if the given time limit is reached. We have two kinds of rewards. The sparse reward gives constant value, constant positive or negative value for if those termination events happen. The dense reward consists of the sparse reward and additionally provides some intermediate guidance for getting closer to the goal, keeping a safe distance to others, and staying at the center of the lane. So now we've seen the core elements of CommonRoad-RL. Here are its key features. The most important one is configurability. So the users can choose the observation space, action space, and rewards using a configuration file. Modularity. So if the desired observations, actions, or rewards are not provided in our environment, our architecture makes the creation of one's own really simple. Usability. So we provide extensive documentations, tutorials, and unit tests to ease the usage of our package. Our toolbox is open sourced at our website, commonroad.in.toom.de. So if you are interested in our tool, please check it out there. Now we demonstrate our tool on the Heidi dataset, which is recorded by a drone on the German highways. So we train each model on around 3,000 Heidi scenarios. All the models are trained using Proxima Policy Optimization, PPO, which is a state-of-art reinforcement learning algorithm. Our baseline model is trained using the sparse reward and the continuous action space for the point mass vehicle model. First, we compare the sparse reward and dense reward. Here we show the learning curves of the goal reaching rate, collision rate, off-road rate, and the timeout rate. As you can see clearly that the agent trained using the sparse reward performed much better than the one with dense reward. A possible reason for that is, first of all, the Heidi datasets, the Heidi scenarios were really simple, so the intermediate guidance from the dense reward was not really needed. And also the dense reward is more sensitive to the coefficients of different reward terms. So the default one we used in our experiments didn't work well and might need more tuning. We compared the discrete action and continuous action space. So both agents converged to the same performance in the end, but the discrete action agent converged much slower since the action values are discretized, so there are fewer actions available during the learning. We also compared two commonly used vehicle models. So the point mass model performed slightly better than the kinematic single track model because the dynamics is much simpler, but its solution might be not drivable since it ignores the non-holonomic behaviors of a vehicle. So in this talk, we introduce a toolbox to solve motion planning problems using reinforcement learning methods. We hope that CommonRoad-RL will ease your motion planning research if you are working on reinforcement learning methods. In the future, we will develop more features for our tool. For example, support multi-agent reinforcement learning, include closed loop simulation with Sumo and Kala simulators. And we will also release open source wrappers for safety layers using formal verification, which could ensure safety during learning. So if you have any questions or any feature requests for our tool, please feel free to contact us at this email address. And thank you for listening.